Module 6, Causality. I find this topic really interesting and I hope you do too. The notion of causality lies at the very heart of epidemiology. A cause is a specific event, condition, or characteristic that precedes the health outcome and is necessary for its occurrence. The idea being that when a causal association is established, a protection and control attitude can occur rather than a mere reaction to the public health crisis. Once upon a time, an enthusiastic young researcher decided to study what makes the sun rise in the morning. Every day, a half hour before sunrise, he dutifully awakened and sat outside in a lawn chair, recording his observations. Every day for that entire year, whether it was cloudy or clear, he heard a rooster crow in the distance. Sometimes 10 minutes before the sun came up, and other times 5 minutes before the sun came up, but the rooster always crowed. After a year of observation, the man was confident that he had solved the mystery of sunrise. He wrote a scientific paper titled "Sound Correlates to Sunrise: What Makes the Sun Come Up?" and in this paper concluded that the rooster's crowing caused sunrise. The article title and abstract were quoted in numerous internet forums. The media picked up on the article and headlines read, "Rooster crowing responsible for sunrise." Over breakfast one morning, you read one of these articles, and using your epidemiology training, you pause and ask, is it real? This example highlights the necessity of not accepting the results of any study, no matter how exciting, at face value. We must first seriously consider non-causal explanations for an association and decide whether the results we are looking at are believable. In this case, we might ask by what biological mechanism did the rooster make the sun rise? Or we might question whether the direction of the relationship was the other way around and the light of dawn caused the rooster to crow. Or was there another reason for the rooster's behavior not related to the sun, such as marking its territory? Just because the two events were associated didn't prove that the rooster caused the sun to rise. In epidemiology, the terms association and causation have very specific meanings. An association is a statistical phenomena relating two occurrences together. However, an association does not assume any meaning to the relationship, only that they occur together. Think of our rooster example. The rooster crowing in the morning happens close in time with the rising of the sun, but there is nothing that directly relates them together in a causal manner. To say two events that occur together are causal means that many other requirements have to be assessed, which I will discuss later. In modules 3 and 4, we established how we measure the occurrence of disease in a population. This helps us to identify aspects of persons, place, and time that might lead to the development of a disease or health-related outcome like an injury. These aspects are termed exposures or risk factors. Basically, to determine if an association exists, we measure the degree to which the rate of a disease or outcome is higher or lower among those with an exposure compared to those without. These ratio measures tell us how many times more likely it is that someone who is exposed to something will develop a certain disease or experience a certain health outcome relative to someone who was not exposed. These ratio measures are fairly easy to calculate. The selection of which ratio measure to use is dependent on the type of data available. Risk ratios, also known as relative risks, and rate ratios are measures of association in cohort studies or randomized controlled trials. Odds ratios are measures of association used in case control and cross-sectional studies. We will spend more time learning how to calculate these measures during the modules on analytic study designs. The risk ratio, or relative risk, is calculated using the cumulative incidence rate. The numerator is the cumulative incidence rate in the exposed, and the denominator is the cumulative incidence rate in the unexposed. The cumulative incidence rate differs from the incidence rate in that it includes in its denominator the population at risk at the start of the study instead of the population at risk at the midpoint of the study. This can be seen here in the equation of A, that's those exposed with the disease, divided by the total exposed A plus B. and then divided by C, that is those not exposed but who have the disease, divided by the total unexposed, C plus D. The rate ratio, as the name suggests, is used when data on the person time at risk is available and is the person time incident rate in the exposed divided by the person time incidence rate in the unexposed. In some study designs, we're unable to calculate an incidence rate for the disease. Therefore, to determine if an association exists, we calculate odds ratios. Just like in horse racing, we calculate the odds of a person with a disease being exposed and the odds of a person without the disease being exposed and divide the former by the latter. A simple way of calculating the odds ratio is to multiply those exposed with the disease by those not exposed without the disease, A times D, divided by those exposed without the disease multiplied by those not exposed with the disease, B times C. The resulting ratio can range from 0 to infinity and has no units. It tells us about the strength of the association between the exposure and outcome of interest. If the relative risk or odds ratio equals 1, this indicates no association. If it's greater than 1, it indicates a positive association. That is, the risk of disease is higher in the exposed compared to the unexposed. If the relative risk or odds ratio is less than 1, it indicates a negative association, and the exposure is a protective factor. There is no universal agreement on what is considered a weak or strong association. Generally, a relative risk or odds ratio greater than 1.5 or 2 would be considered moderately strong, and an effect greater than 3 would be strong. As illustrated by the rooster and sunrise story, not all associations are causal. Alternative explanations for observed associations are chance, bias, and confounding. An association may arise by chance. When we observe an association between two groups, we can carry out a statistical test known as hypothesis testing. The course text by Merrill describes this process in detail. The results of these statistical tests often take the form of a p-value, which gives us an idea of how likely it is the association is real, or that the results might just be due to random sampling error or chance. The p-value tells us the probability that we would have seen a difference as big or bigger than we did if there was really no difference between the groups. Conventionally, results are considered to be statistically significant, that is, unlikely to have occurred by chance, if the p-value is less than 0.05. This means that if you conduct 100 studies on a given exposure outcome association, on average, 5% of the time we would expect the results to falsely report a significant association when there really isn't one. The confidence interval is another way to evaluate statistical significance. It is a range of values around the observed effect estimate, the relative risk or odds ratio, that is likely to include the true point estimate. The most commonly used confidence interval is 95%. If the confidence interval doesn't include 1, no association, you can conclude that the association is statistically significant and unlikely to have arisen by chance. In addition to considering the statistical significance of an association, we should also consider the sample size and whether the study has enough power to detect with sufficient precision if an association exists. It's possible that an exposure causes a disease, but that the study was too small to detect the effect. As I've said before, unlike laboratory scientists who can control all aspects of their study, epidemiologists have to work within the complex environment of real life. And as a result, no epidemiological study will be free from error or bias. Therefore, when designing and conducting a study, it's important to take steps to minimize error as far as practically possible, and then assess the likely effects of unavoidable error on the observed association. In epidemiology, there's dozens and dozens of names or labels given to the kinds of biases that can occur. But for the most part, these can be classified as bias related to the selection of participants for study or to the measurement of exposure and/or outcome. We will learn more about these types of bias in future modules. You were introduced to the concept of confounding in Module 4. This is essentially a distortion in the observed association due to a third factor, that is an independent risk factor for the disease, is associated with the exposure of interest, and does not lie on the causal pathway. Confounding should always be considered as a possible explanation for an observed association. Again, we will learn more about controlling for confounding in future modules. Once we've considered the alternative explanations of chance, bias, and confounding for an observed statistical association and believe that it's true, the next step is to determine if the association might be causal. Causality can never be proven with 100% certainty, but by a process of developing and testing hypotheses, epidemiologists can provide high-quality data to support or refute the hypotheses, which together with critical reasoning can provide evidence to support causality. You were introduced to several conceptual frameworks for causality in Module 2, including the epidemiological triangle, Rothman's pies, disease transmission, and the webs of causation. In practice, when considering the cause of a disease, we're often dealing with a component cause. You might recall in Rothman's causal pies, where the individual pieces of the pie were referred to as a component cause. Several component causes may be required to get a complete pie, which is referred to as a sufficient cause, resulting in the disease. A component cause that is always associated with a disease is called a necessary cause, as the disease cannot occur without it. Component causes can be further classified as predisposing, reinforcing, enabling, and precipitating factors. Predisposing factors are factors or conditions already present that produce a susceptibility or disposition in a host to disease or condition without actually causing it, such as age, immune status, or people's knowledge, skills, preferences. Reinforcing factors are the factors that help aggravate and perpetuate behaviors, disease, conditions, disability, or death. They can be positive, such as social support, or negative, such as economic burdens. Enabling factors are antecedents to behaviors, disease, conditions, disability, or death that allow it to be realized, such as living conditions or presence or absence of health services. Predisposing factors are factors essential to the development of the disease, condition, injuries, disabilities, and death, such as infectious agents or lack of helmet or seatbelt use in motor vehicle accidents. Various guidelines have been proposed to assist epidemiologists in evaluating causality. There are many similarities among them, but the best known was proposed by Sir Bradford Hill in 1965. He proposed a set of 9 criteria that should be considered when assessing if an association is causal. These criteria were: number 1, strength of association, as indicated by the size of the relative risk or odds ratio. The larger the relative risk or odds ratio, the more likely it is that the association is real and not due to bias or confounding. As mentioned previously, a relative risk or odds ratio greater than 3 would be considered a strong association. However, just because an association is weak doesn't mean that it's not causal. The second criteria is consistency. If the same association is observed across a range of studies of different types and/or in different populations, then it's more likely to be a real effect. However, again, lack of consistency does not necessarily rule out causality, as so-called heterogeneity might be due to differences in study design or quality, or differences in the populations included in different studies. The third criteria is specificity, which reflects the idea that a specific exposure results in a specific outcome. For example, cigarette smoking is only associated with lung cancer. However, we know that this is not the case and that smoking is related to many different diseases. Nonetheless, smoking is not associated with all diseases, so there is still some level of specificity which can inform an evaluation of causality. Bradford Hill acknowledged that this criteria should not be given as much weight as others when evaluating causality. Fourth, temporality, meaning that for an exposure to cause a disease, it must precede the development of the disease. This criteria is an absolute requirement when establishing causality. Fifth, biologic gradient is another way of referring to a dose-response relationship. If a factor does cause a disease, then the risk of developing the disease is likely to increase with greater exposure to the factor. The amount or dose is a function of both the level and the duration of exposure. However, the dose-response relationship may not be linear, and there may be a threshold effect above which an exposure will cause a disease. The sixth criteria of biological plausibility refers to a likely mechanism through which the exposure might cause a disease. The seventh and eighth criteria of coherence and analogy are similar to the second criteria of consistency, meaning that the observed association should not conflict but be analogous with the known facts. Finally, the ninth criteria to consider is experimental evidence, which refers to supporting data from studies in animals or other organisms, or from intervention studies in humans. Consideration of these 9 criteria can help us decide whether an association is likely to be causal. Sometimes the decision is clear-cut, like in the rooster example, but sometimes it's not so straightforward. Remember, causation cannot be proven, so there can be no right answer. To quote Bradford Hill himself, we must ask, is there any other way of explaining the set of facts before us? Is there any other answer equally or more likely than cause and effect?